All right, welcome back. So next up is the 5.4, the candidates test. So we're going to use this in conjunction with what's called the extreme value theorem. So we've talked about intermediate value theorem and mean value theorem. The extreme value theorem is for a function that's continuous on a closed interval. Then it must have a maximum and a minimum on that interval. All right, but the key is it has to be continuous, including a and b from a to b. So if there's a hole at A or a hole at B, then the extreme value theorem cannot apply. If there's holes or jumps or vertical asymptotes in between A and B, then the extreme value theorem cannot apply. But assuming the function is fully continuous, there has to be a max and a min. Which means while we do talk about the idea of relative max and relative mins, so like if we have a graph that looks like this right here, let's say our curve does something like this, like that's our cubic function right there. If we take a screenshot that only talks about this interval right here, so from whatever this, let's say this is our B value, let's say this is our A value, we can see while this is a maximum point and this is a minimum point, those do not represent the highest and lowest points of the graph. It turns out at the endpoints they are. So that's what the idea of relative versus absolute extrema is talking about. So absolute, so relative extrema or local mins, local maxes are occurring at the peaks and valleys. These occur at the critical points of your function. Whereas the absolute extrema, also called global min and global max, is the complete lowest and complete highest value you have on a given interval, which can occur at the critical points, certainly possible, or it could occur at the endpoints. So the way we figure that out is whether or not the absolute max or min occurs at the critical point or at the endpoint is use what's called the candidates test. This is where we first find our critical numbers, so our derivative set equal to 0, solve, and then we substitute those critical numbers and, this is critical, and the endpoints of the interval back into the original function. We will then compare those y values, those function values. The lowest y value we have is the absolute min, the highest is the absolute max. Which means, this will occur plenty of times, the critical numbers themselves will not yield global or absolute max and mins, while they will be locals. So it's a little bit different from just your relative max min, so you have to pay attention to the context clues. If they're talking about critical points, talking about relative min, relative max, local, that kind of stuff, you're finding your first derivative test or second derivative test to figure out whether it's a max or min. We're talking about what is the highest point in the graph, what is the lowest point, or the maximum speed something is occurring at, or whatever it is. They want the absolute highest, regardless of whether it's a critical point or not. So we're going to do a couple examples of that. So we'll stick with a simple polynomial. F of x is x cubed minus 3x squared plus 2 from 0 to 4. So we have to first find our critical points. We find our derivative, which would be 3x squared minus 6x. We then factor the 3x away from the expression, leaving x minus 2, and we set that equal to 0. So the individual factors, 3x and x minus 2, are set equal to 0, giving us critical points at 0 and 2. Now the critical points have to fall inside the interval, which is from 0 to 4, which they both do. But if this had been, let's say, the interval was from 1 to 4, then we would not consider the 0 because it's not part of the interval. So the critical point has to fall inside the interval in addition to using the endpoints themselves. So what we're going to go ahead and find is f of 0, f of 2, and f of 4, the endpoints and the critical points. So f of 0 goes back to the original, so 0 cubed minus 3 times 0 squared plus 2. We're going to get 2, because all those zeros just go away. F of 2 would be 2 cubed minus 3 times 2 squared plus 2. That gets us 8 minus 12 plus 2, which is a negative 2. So that's currently lower than 2, so that could be our absolute min. F of 4, we have 4 cubed minus 3 times 4 squared plus 2. So we get 64 minus 48 plus 2, so we get 18. So this tells us, kind of running out of room here, we'll do it up in the top left corner. We have an absolute min at quarter point, will be the lowest point's negative 2, so it's 2 comma negative 2. Whereas our absolute max at 418. So depending upon how they phrase the question, you might be asked for the location of the min or max, which would be the absolute min occurs at x equals 2, the absolute max occurs when x equals 4. Then I'm going to ask you for the value of the min or max, so what is the lowest value, what is the highest value. So the lowest value is -2, the highest value is +18, or they might want the full coordinate point. So just pay attention to the context of the question, what they actually want. When in doubt, give a full coordinate point and see what that does for you. So that's a simple polynomial. Let's take a look at a rational function. This one requires our quotient rule. So our quotient rule tells us to do low d high. So x squared minus 1. Derivative of the top is 0 because it's a number. Minus high d low. So derivative of x squared is 2x over low low. So x squared minus 1 squared. That gives us negative 6x over x squared minus 1 squared. Our critical points, we would worry about the numerator, negative 6x equals 0, and we'd worry about the denominator where the derivative is undefined. So x squared minus 1 equals 0 when x is plus or minus 1. Now, you're looking at the critical point 0 does not fall in between -7 and -3, so that's actually not a valid point to worry about then. And positive and -1 also don't fit in the interval, but even if they did, we wouldn't use them, because if you go back to the original, those would be vertical asymptote locations. So again, it is important to always consider when the derivative is undefined, but a lot of times there won't be actual points you can use simply because they're going back to a vertical asymptote, so it's not really relevant. So we're not going to use anything here. We're going to only use the endpoints. Because in this interval, we're either always increasing or always decreasing. There is no peak or value that's occurring here because the interval does not include the actual critical point location. So we have f of -7, which would be 3 over -7 squared minus 1. 3 over 49 minus 1 is 3 over 48. Reduces to 1/16. And f of -3 would be 3 over -3 squared minus 1, which is 3 over 9 minus 1, which is 3/8. So 1/16 is definitely smaller, so we have our absolute min at -7 1/16. And then we have our absolute max at a larger value, which would be at -3, 3/8. All right, so it's possible that your critical point not actually be relevant towards the candidate's test result. Always use the endpoints, and any critical numbers that do fall inside the interval should also be used. All right, so looking at our last example here, we've got a trig function. Always important to be able to do trig derivatives and remember values from your unit circle here. Now, trig functions will always give you interval anyway for the first or second derivative test because there's an infinite set. So you always will have an interval, but here we generally shorten the interval for the candidate's test. We don't have too many locations going on that we have to consider. So our derivative, sine becomes cosine. We have to have a 2 to derive the 2x, so it's a -2 cosine of 2x. We said equal to 0. So ultimately, the -2 didn't even matter. So if you mess that part up, you can kind of get a little lucky here for this particular question. Cosine is equal to 0 at 2 points, pi over 2 and 3 pi over 2. So we divide that by 2, and we get x equals pi over 4 and 3 pi over 4. Now, 3 pi over 4 falls outside the range we want, pi over 6 to pi over 2, so I got to cross that out. Now, it's possible, because again, there's an infinite set, you always have to consider negative and positive coterminal angles. Obviously, I'm not going to consider any more positive coterminal angles because anything after 3 pi over 2 is also definitely going to be crossed out. So I should consider a coterminal or two before pi over 2. So we put in negative pi over 2 in first. That would give us a negative pi over 4, and, well, it needs to be a positive angle, so that's also crossed out. So the only critical point that matters for this particular interval is pi over 4. So always be careful with your coterminals of the trig. Make sure you include enough values that fit in the interval. If you're ever unsure, just keep on adding more positive and negative both directions until you eventually conclude so you've got enough. So we then do our values at pi over 6, pi over 4, and pi over 2. So 2 times pi over 6 is pi over 3. And sine of pi over 3 would be root 3 over 2, but there was a negative, so it's negative root 3 over 2. All right, so we have f of pi over 4, so negative sine of 2 times pi over 4 becomes negative sine of pi over 2, which is a -1, because sine of pi over 2 is +1. And then finally, f of pi over 2, negative sine of 2 times pi over 2 becomes negative sine of pi, which is 0. So the absolute max is pretty easy to see. Absolute max is clearly going to be at the 0 spot. That's the highest value because the other two are negatives. So we have absolute max at pi over 2, 0. Now for the absolute min, again, if you got a calculator, it's pretty easy to see which one is bigger or smaller. Just do a quick decimal for the negative root 3 over 2 and compare it to -1. Without a calculator, you need to recognize that negative root 3 in general is smaller than root 4, and root 4 would be 2, and 2 over 2 is 1, so therefore root 3 over 2 is smaller than 1, but since it's negatives, that means negative 1 is really smaller. All of that to say, negative 1 is the smallest value, so our absolute min occurs at pi over 4 comma negative 1. All right, and those are our final candidates test answers. So again, pretty much any question you saw from either 5.2 or 5.3, 5.3 especially because that's where we're talking about the whether it's a relative max or relative min, you could also have done a candidates test if they wanted the absolute max or absolute min. Now, certain examples you would not have been able to figure out. For example, when they gave us the derivative, we really can't figure out the highest and lowest points without knowing the original function. And going backwards like that is the basis of Unit 6, which we'll get into obviously next unit, but we can't go backwards just yet. All right, so that's it for 5.4. So this is really everything with the first derivative. We're going to start talking about how we can use the second derivative for certain parts of the graph. Not the second derivative tests, but using the second derivative to find other stuff. So I'll see everyone next time for that.